So carrying on from where we left off last time, we have our expression for the period here. And of course, we know that frequency is 1 over the period. So we have the expression f equals omega over 2 pi then, which I have stuck away on the side here to save me doing the whole symbol thing again. So we said earlier that because the direction of the velocity is changing, then it must be accelerating. And we can, by looking at a small change in the position, small change in the angle, we can derive an expression for the acceleration. But I don't think we need to do that. If when we get back to school you want to see that done, I'll do it, but I'm not going to try and do it here. Mainly because the amount of faffing about with the diagram to get the symbols on is more than I can cope with, really. So there is a derivation here for this, which I'll do for you at school should we ever get back. So a is v squared over r is the acceleration. Now, from Newton's second law then, we have F equals ma. So we have F equals mv squared over r. And of course, from our expression v equals r omega, we can rewrite that to be F equals mr omega squared. Now these are exactly the same expression, it's just that we've substituted v equals r omega here, in here, to give us v is r squared omega squared. And then if you divide that by r, you get F is mr omega squared. So another important expression for you there. Oh, too far. Let's take that back. So F equals mv squared over r, or F equals mr omega squared. Now, this is a force towards the center of the circle. I should have said the acceleration is towards the center of the circle. It is a centripetal, or if you like, centripetal. I don't like. Centripetal is how I like to pronounce it. So centripetal acceleration. That's an important term. That means towards the center of the circle. And of course, because it's a centripetal acceleration, it is also a centripetal force. Spelled correctly. So centripetal means towards the center of the circle. Now, I'm going to say there is no work done by this force. If I can spell these words. There is no work done by this force. And my question to you is, how do I know that? So I've write that down. And to save me typing it again. What implications does that have? I seem to have shoved that down. I didn't mean to do that. So I'm going to ask you to stop the video there and think about those questions. There's no work done by the force. How do I know? And what implications does this have? How do you see this working in the real world? What would happen maybe if it wasn't true? So stop the video, think about that, and then start the video again. So, how do I know that this is doing no work? Well, if you think about work done is the size of the force times the distance moved along the line of action of the force. Now, the force is always towards the center of the circle, and the motion is always along these lines here. These are tangents, of course. So the tangent, by definition, is at right angles to the radius. The force is along the radius, and so the force is at right angles to the motion. There is no motion along the line of action, and so there is no work done. There you go, me typing madly and getting it wrong. So you should now be relating the work that you have done on the other side of the course on work and energy, and the work you did at GCSE on work and energy to this. This synthesis, this connection between different parts of the course is hugely important for your ability to answer those questions that come your way. You need not to have these things in little compartments in your mind, but be making the connections between the different bits of work. So here we have something moving in a circle. It's not doing any work. The force is not doing any work. And you should be able to see that it can't be doing work because the direction of the force towards the center of the circle is at right angles to the direction of motion. And so because there is no motion along the line of action, there is no change in motion along the line of action, there is no work done. So that's my first of the two questions. And I said, what implications does this have? Well, if the force was doing work, work, of course, is a change in energy. Work is force times distance moved along the line of action of the force, and the amount of work done is the amount of energy converted. So, if this force was doing work, energy would be being converted. So, if something moving in a circle was having work done on it by that centripetal force, then it would be losing energy, or gaining energy perhaps, but there would be work done, which would mean it could not maintain that circle unless there was an energy input from somewhere. So if you think about the Earth around the Sun, this simply wouldn't work. The Earth would not maintain that orbit if the centripetal force, caused by gravity, of course, if it was doing work, then there would be movement along the line of action, and the Earth would spiral into the Sun. So the fact that no work is being done is crucial, actually. And if you think about artificial satellites, if work was being done by the weight of the satellite in pulling it into the Earth, then there would have to be a constant input of energy to maintain the satellite in orbit, which would mean the satellite would have to have an energy source, which would make things much, much more difficult. So the force is doing no work. It cannot be doing work because the direction of motion and the direction of the force are at right angles, and that is crucial. Now, we're going to be looking at lots of things moving in circles as we move into the second year, further into the second year of A Level here. We're going to look at gravitational fields, electric fields, magnetic fields, and things move in circles in all of those. So you're going to need to be able to connect the work we're doing here on circular motion to all of the work we do in fields as well. So just bear that in mind, more of that synthesis. Circular motion comes up a lot in fields, so bear that in mind. So moving on then to look at an example, I have a diagram that I want to copy over. I don't know whether I can do that just, no, okay. So here is my diagram, which I want to crop. Just give me a moment while I do that. So here we have a stone being spun in a vertical circle. I don't want that to be bold, really. So the stone, mass m kilograms, is spun in a vertical circle, radius r meters, at constant speed, v meters per second. Okay, so there will of course be a tension in the string. Here's my string in 3 different positions, right? There will be a tension in the string. Here we have mg acting down. I haven't got that arrow in because I couldn't manage to make the arrow collinear with this one. So you have mg acting vertically down because it always does. And so the centripetal force, which is the resultant force towards the center of the circle, is the tension, which of course is towards the center of the circle, minus mg. So T minus mg equals my resultant force. In this position, well, the weight is vertically down. It has no effect horizontally. And the centripetal force here is horizontally. So it is T equals the centripetal force here. And then here, well, you have mg acting vertically down as always. So T plus mg equals the centripetal force. So there you have 3 positions of this stone in the vertical circle, here, here, and here. Here, the centripetal force is T minus mg. Here, the centripetal force is T. And here, you have both t and mg vertically down, so t plus mg equals f. Now, remember what we said before, that f is mv squared over r. Now look at this. M is a constant, v we have defined as a constant, r is a constant, so f has to be a constant, right? So t plus mg equals f, t minus mg equals f, m, g, f are constants, so t must be changing, right? T must be changing as the stone goes around the circle now. You would know that if you've ever spun something reasonably heavy on a string vertically, and if not, why not? You would know that the tension changes. You know where the tension is greatest and least in that spinning of a thing on a circle, in a circle, on a string. I'm not going to recommend you do this because injuries could abound. So for health and safety reasons, I'm not going to suggest you do it. But if you have done it, then you'll know that the tension does change as the string goes around in that circle. So the first question is, where is the string most likely to break? And the next question is, what is the minimum speed for the stone? Oh, the typing's poor. To perform a circle. So I'm going to ask you to stop the video, come up with your answers to the questions, and then come back to me. Okay? So, where is the stone most likely to break? Well, where is the tension greatest? If you look here, if we were to make t the subject of this equation, you'd have t equals f minus mg. So, at the top, t equals f minus mg. At the bottom, t equals f plus mg. So at the bottom, t is the greatest, and that's where the string is most likely to break. Hopefully you can see that. As you spin the stone faster and faster and faster, the centripetal force required, if you think about it, gets greater. I mean, you can do that from the maths up here. V is mv, F is mv squared over r, so if I make V bigger, F gets bigger. If you think about it from a qualitative point of view, the faster the stone is spinning, the quicker it's coming round the corner of the circle. I know the circle is just one big corner, you know what I mean. And so the faster, the bigger the rate of change of the velocity. The velocity is bigger, but also the rate at which the velocity is changing is bigger. And so the rate of change of velocity is bigger. and so the acceleration is bigger, so the force must be bigger by Newton's second law. So as you make the stone spin faster, F gets bigger, and so T must get bigger at the bottom here, and so that's where the stone is most likely to break, or sorry, the string is most likely to break. So, what is the minimum speed for the stone to perform one circle? Well, at the top of the circle, if the stone is traveling, well, that's supposed to be an R with the A, at a minimum speed T will fall to 0 just as the stone goes over the top, right? So if we take our expression for tension at the top, T is F minus mg, so that equals 0, so F equals mg, but F equals mv squared over r. Let's make that not bold and black. So the m's will cancel, and we have v squared over r equals g. So we have v squared equals rg. So we have v equals rg to the half. So there is the minimum speed for a stone moving in a circle radius r, vertical circle radius r. That is the minimum speed for it to continue that circle. Hopefully that's clear to you. And that's the end of my second video on circular motion.